Good day, viewers. It's good to have you back in class today again. My name is Dr. Chris Isekaibe. I will be taking us today on a topic, a continuation of numerical integration. There is a part that we really need to know about numerical integration. Today, I want us to really look at the numerical integration of trigonometric and exponential functions. The way we integrate trigonometric functions is quite different from the way we integrate other algebraic expressions or equations or functions. So permit me, we shall be taking a very simple example. By the time you understand that example, you will be able to carry out any integration on trigonometric functions. Once again, please subscribe to my YouTube channel, Dr. Chris Isekaibe. Click on the notification button so that anytime I upload a video, you will have an alert. Share my YouTube videos on your social media platforms. Like my videos, and as you do, God will bless you. In our last class, talking about numerical integration part 2, when we use the Weddle's rule, the Simpson's 3/8 rule, I displayed my contact on the board and my email address. If peradventure you want to contact me, you want us to work together as a team, to write papers together, you want me to be a reviewer in your journals, or you want me to be a team member in your research institute, whatever you want me to do, I believe in sharing of knowledge. So the essence of this YouTube channel is to share knowledge across the globe. I found it that mathematics and statistics topics are dreaded by some individuals across the globe. So I decided to come with this channel so that I will be of help, I will be of assistance in my own little way. So please contact me if you have anything you want us to do together. So we shall be looking at the solution of trigonometric and exponential functions, integrating them numerically. Now, before we move further, let us quickly take a simple problem. If, for instance, you are given a problem like this: integral pi to 0 cos x dx. Now, this is a definite integral and it has a trigonometric function cos x. When we talk about trigonometric functions, we're talking about functions that have cosine, sine, cotangent, secant, cosecant, and the rest of them. Those are equations or functions involving trigonometric functions. The way we integrate them is quite different from the way we integrate other algebraic expressions. Now, the first thing we need to know is how, if you look at this, although we'll first of all go ahead and get the true solution. Let us get the true solution of this particular problem. True solution. If I'm to integrate this, I'm going to have, if I integrate cos x, I'm going to have sine x. So this will now be equal to sine x. Of course, the upper function is there, then the lower, the upper boundary is there, then the lower boundary is there. Then this will now be equal to sine pi minus sine 0. Please note, in degrees, pi is equal to 180 degrees. Then in radian, pi is equal to 22 over 7. If you look at this, so now if we now go ahead and check the value for sine, so this will now be equal to sine 180 degrees minus sine 0 degrees. Sine 180 degree is 0 minus sine 0 degree is 0, so our answer to this particular problem is 0. So have this at the back of your mind. Pi in degrees is 180 degrees. So this value is running from 0 to pi. That means from 0 degree to 180 degrees. Anytime you are dealing with trigonometric functions, have it at the back of your mind that you are dealing with degrees. The trigonometric functions, they deal with degrees. You can have 30 degrees, 40 degrees, sine 30 degrees, cos 40 degrees, sine 50, sine c, and so on and so forth. So we deal in degrees. Now, pi means 180 in degrees, and pi means 22 over 7 in radian. Like when you, for instance, you want to calculate the area of a circle, the area of a circle is pi r square. That pi there, the measurement is in radian, and that is 22 over 7. So when you see a trigonometric function and pi is mentioned, you know that pi, they are talking about 180 degrees. So in degrees also, if I say 2 pi, for instance, this is the same thing as 2 into 180 degrees, and that is equal to 360 degrees. So you should know that. If I say 3 pi's in degrees, it means 3 times 180 degrees, and so on and so forth. But in radian, pi means 22 over 7. So please take note of this solution. The true solution or the theoretical solution to this particular problem, integral from pi to 0 cos x dx is equal to 0. Is equal to 0. Take note of that particular solution, the answer. We shall be making use of it when we want to calculate our truncation error. Now let us use our numerical methods. The first method we shall be using here is the Weddle's formula, the Weddle's rule. We shall be using the Weddle's rule. Now, for you to use the Weddle's rule, you must understand that here our n is equal to 6. That's why you see the formula runs from y0 to y6. So our h is given to be b minus a all over n. You can see now, when we are dealing, that means for this particular problem, if we have the problem as integral pi to 0 cos x dx, this simply means that our y is equal to cos x. That is what it means. It means that our y, because the problem is y dx. So now the place of y is cos x, and y is a function of x. So we have explained this again and again. So what we need to do here is to get our h. Now, if your y is cos x, that means it's a trigonometric function. Y is a trigonometric function. That means getting this y0 to y1 will involve degrees. Then there is another h outside of this y0. Look at it. That h does not involve trig functions. It does not involve a trigonometric function. So the h there is in radian. That is what makes the integration of trigonometric function to be a bit tedious. So you are going to have 2h now. The first h will be for the trigonometric function. When we have the degrees, then we are going to have the second h in radian. So I have the first h in degrees. So now in degrees, our h is equal to b minus a over n, and here our b is the upper bound, which is pi. Remember, in degrees, pi is equal to 180 degrees And in radian, pi is equal to 22/7. So this one is in degrees. This one is in radian. So you should take note of all this. So in degrees, pi is 180 degrees. In radian, pi is 22/7. So now our b will now be pi, which is 180 degrees all over minus a. A is 0 all over n. Our n is 6. So it's equal to 180 degrees over 6, and that is 30 degrees. So in degrees, our h is 30 degrees. Then in radian, our h will be equal to, now remember, pi is 22/7 in radian, because here we cannot use the h that we got for the using 180 degrees, because this h here is in radian. So here you are going to have 22/7, that is b, minus a of, again, is 0 all over 6. So if you have this will be 22/7 divided by 6. So this will be equal to 22/7 times 1 all over 6 is equal to 22/42. So we are going to take it in 5 decimal places. So it will be 22/42. That will be 0.5238. 5238. Let's take it to 5 decimal places. 2381. So this will be our h in radian. Our h in radian is 0.52381. Our h in degrees is 30 degrees. So we are now going to see how we can put all this together. First of all, we create our table. Then we now use the Weddle's formula to carry out our calculation. So please take note of this. Now we want to go ahead to create our table. We want to go ahead and create our table. Table having values of x and values of y. Now remember, our y is equal to cos x. So h in degrees is 30 degrees. Then h in radian is 0.52381. 52381. So take note of that. So we have the value of h in degrees and h in radian. Now let us go ahead and create our table. So we are creating table in x and y. So we have our x, we have our y. Now, because this is a trigonometric function, our x will run from 0. You have it like this: 0 less than or equal to x less than or equal to 180 degrees, because it runs from 0 to pi, and pi in degrees is 180 degrees. And now, because our y is cos x, our x will be increasing with 30 degrees. So we are using degrees. So it's starting from 0 when x is 0, then you add 30. When x is 30, you add 30 again. When x is 60, you add 30 again. When x is 90, you add it again. When x is 120, you add 30 again. When x is 150, you add it again. When x is 180 degrees. All in degrees. All in degrees, including the 0. All in degrees. Now we want to get the corresponding value for y. The corresponding value for y when x is 0, cos 0 will be 1. You press your calculator, cos 0. When x is 30, cos 30 is 0.8660. When x is 60, cos 60 will be 0.5. When x is 90, cos 90 will be 0. When x is 120, you are going to have cos 120 will be minus 0.5. When x is 150, cos 150 will be minus 0.8660. Minus 0.8660. Then when x is 180, cos 180 is minus 1. Cos 180 is minus 1. So permit me to have these values like that. So you can, if you want us to rule it so that it will be neat, we can go ahead and do that so that we can distinguish them among themselves. So you see this, and so on and so forth. This is beautiful. So you can see now we have created a table having values of x and y. So permit me to go ahead to use this Weddle's formula or Weddle's rule to carry out this integration using this table. We have been able to create the table. So integral from pi to 0 cos x dx will now be equal to 3h. Now we are not using the h in degrees. We have used the h in degrees to get the values for y and x. Now this h here is in radian. That's why we are getting a different value for h in radian. So this will be 0.52381 all over 10, then bracket open. Why not? Now it's very simple to note. You can take this to be your y naught. Call this your y1. Call this your, okay, let me put it inside. So let's call this our y naught, y1, y2, y3, y4, y5, y6. So you can see that it must, because h has been able to spread the value of x from the lower boundary to the upper boundary, then you will get it up from y0 to y6 as needed in the Weddle's formula. So now what is our y0? Our y0 is 1 plus, we have 5y1. Our y1 is plus 5 into 0.8660. Then plus y2. Our y2 is 0.5 plus 0.5 plus 6y3. Our y3 is 0.6 into 0 plus y4. Our y4 is minus 0.5. Then plus 5y5. Then plus 5 into y5 is minus 0.8660. Then plus y6, permit me to write it here, plus y6, our y6 is minus 1, plus minus 1. Then you cover the entire bracket. So breaking it down, if you say 3 times 0.52381 divided by 10, you are going to have 0.15714 into this one will be 1. 5 times 0.8660 will be plus 4.33. Then of course plus 0.5. Then 6 times 0 is 0 plus 0. Then of course minus times plus will be minus 0.5. Then 5 times minus 0.8660, that will give us minus 4.33 minus 4.33, then of course minus 1 plus it will now be minus 1. So you can see we now have all this. So carrying out this arithmetic, you will now see that everything that we have here will now be equal to 0.15714 into 0. Look at it, this one here, we cancel this one. 4.33 we cancel, minus 4.33 plus 0.5 we cancel, minus 0.5. So everything in this bracket will be 0. So carrying out this into this multiplication, this will now be equal to 0. You multiply anything by 0, you get 0. So you can see now we have successfully used the Weddle's rule to solve this particular problem, and we arrived at 0. So meaning that our truncation error is very important we calculate it, will now be the true solution minus the numerical solution. That will be 0 minus 0, and that is equal to 0. So the Weddle's rule is error-free for this particular problem. The Weddle's rule is error-free for this particular problem. I hope you are following the calculation, and I hope you are getting it squarely. So the Weddle's rule is error-free for this particular problem. So permit me to quickly use another rule. This time around we shall be using the Simpson's 3/8 rule. The Simpson's 3/8 rule. So the table will still be of good use to us. So permit me to rub off this part of the board so that we can quickly go ahead and do that. The table is of use to us, so permit me to still clean this part of the board. Permit me to clean this part of the board also, so that we can use the Simpson's 3/8 rule to solve the same problem. The Simpson's 3/8 rule. Now, the Simpson's 3/8 rule. The Simpson's 3/8 rule is very easy to write. You have it as integral xn to x0 y dx is equal to 3h/8. We have used it before, into y0 plus 3y1 plus 3y2 plus 2y3 plus 3y4 plus 3y5 plus 2y6, and you keep on going. Plus, of course you continue, plus 2yn minus 3 plus 3yn minus 2 plus 3yn minus 1 plus yn. That is the Simpson's 3/8 rule. Now it will interest you to know that for this particular problem here, our h remains the same. The h we shall be using outside the y0 is gotten in radian using 22/7. Again, look at the Simpson's 3/8 rule. The y0 is left outside, the yn is also left outside. The coefficients are 332, 332, 332. Even before you get to the third y value of y before the last y is 3, 3, and then the last value of y. So please permit me to solve this problem using this. So our integral pi to 0 cos x dx will now be equal to, of course, our h gotten in radian is 0.52381. So we are going to have 3 into 0.52381 81 all over 8 into bracket open. Now, what is our y1? Our y0 is 1 plus our y1 plus 3 into y1 0.8660 plus 3 into y2 plus 3 into 0.5 plus 2 into y3 plus 2 into 0. Then it continues like that. Then plus 3 into y4 plus 3 into y4 is minus 0.5. Then again plus 3 into y5 minus 0.8660. Then plus the last value of y, which is y6 plus minus 1 in bracket. Then you close the bigger bracket. So you can see here again that when we open the bracket, we are going to get something meaningful. So our integral pi to 0 cos x dx will now be equal to, when you multiply 3 by that particular value and divide it by 8, you are going to have 0.19643 into that is 0.19643 into, when you multiply, you carry out this will be 1 plus 3 into 0.8660 is 2.598 plus 2.598, then plus 3 times 0.5 will be 1.5 plus 2 times 0 will be 0. Then 3 times minus that will be minus 1.5. Then 3 times this will be minus the same value, 2.598. Then minus 1 times plus it will be minus 1. So you close the bracket. You see that? It's as simple as that. So by the time you come now, you can see that 1, we cancel out 1 minus 1, 2.598 minus 2.598, 1.5 minus 1.5, everything inside the bracket again will become 0. So this will be equal to 0.19643 into 0. So again, we are getting 0. So our truncation error will now be equal to the true solution minus the numerical solution is 0 minus 0, and that is equal to 0. So you can see again that the Simpson's 3 over 8 rule is 0. Has given us 0 as the solution, and the truncation error is now 0. So the Simpson's 3 over 8 rule is also error free for this particular problem. Now we shall be looking at the trapezoidal rule. We want to make use of the trapezoidal rule to solve this same problem. So permit me to clean this part. The trapezoidal rule. We want to use the trapezoidal rule to solve this same problem and see if it will also generate the required results. We'll see if it will generate the required results. So now, the trapezoidal rule. The trapezoidal So the trapezoidal rule is given as this integral xn to x naught y dx and equal to h over 2 into y naught plus 2 into y1 plus y2 plus y3 plus yn minus 1 all in bracket, then plus yn, then the bracket is closed. So this is the trapezoidal rule. Now, using it to carry out that integration, we have integral pi to 0 cos x dx, and that will be equal to, now the h again is in radian, and that is 0.52381, so that will be 0.52381 all over 2, in bracket open. Our y naught again is 1 plus 2 into y1 is 0.8660 plus y2 0.5 plus y3 which is 0, then plus y4 plus minus 0.5, then our y5 will be plus minus 0.8860. Then of course you have plus minus 1, then you close the bracket. So now you are going to have integral pi to 0 cos x dx to be equal to, if you say 0.52381 divided by 2, you are going to have 0.26191, 0.26191. Then when you open the bracket, you are going to have everything here. When you add, look at it, of course this minus 0.5 will cancel out, minus 0.5 minus 0.8866, sorry, minus 0.8660 we cancel this. Then of course everything inside this will be 0, then 1 minus 1 will be 0. So again you are going to have everything in bracket to be 0. So this times 0 again will give you 0. So the truncation error will be equal to the true solution minus the numerical solution, and that will be 0 minus 0, and again is 0. So we have succeeded in also using the trapezoidal rule to solve this problem, and we arrived at 0. Now lastly, we shall also use the Simpson's 1/3 rule. Let us quickly use the Simpson's 1/3 rule to solve the same problem. We are still solving just a problem on trigonometric function. We are saying how we can use these various formulae to carry out numerical integration. We are saying how we can use this various numerical method to solve a trigonometric, or to integrate a trigonometric function. Now lastly, we are using the Simpson's 1/3 rule. The Simpson's 1/3 rule. So it's given as integral xn x naught y dx, and this is equal to, that will be h over 3 into y naught plus 4 into y1 plus y3 plus y5 plus yn minus 1 plus yn minus 1, then permit me to continue here, plus 2 into y2 plus y4 plus y6 plus yn minus 2, then you close the bracket, of course, plus yn, then you close the bigger bracket. So this is how the Simpson's 1/3 rule is used. Now let us apply it to solving the problem integral pi to 0 cos x dx will now be equal to, note again, our h gotten in radian is 0.52381, so it will be 0.52381 all over 3. Then you open your bracket, there is a 1 here, then 4. Okay, no, our y naught is 1 plus 4 into listing. For the Simpsons 1 over 3 rule, you can see 4 multiplying the sum of the values of y in the odd positions, y1, y3, y5, down to yn minus 1. And you can see 2 multiplying the sum of the values of y in the even position, y2, y4, y6, down to the second to the last. But now the y0 and the yn are reserved. They are not part of it. So now 4 into y1, what is our y1? Our y1 is 0.8660 plus, of course, what is our y3? Our y3 is 0 plus, of course, we have y5 second to the last. That will now be minus 0.8660. Then you come again, you now say plus 2 into, what is our y2? Our y2 is 0.5 plus, what is our y4? Our y4 is minus 0.5. You can see why I labeled the table, so that it will be easier for you to pick or locate the various values. You can see that I've already labeled it y0, y1, y2, y3, y4, y5, y6. Doing that, it will be easy for you to locate. Now you cover this bracket, then of course plus our yn. Our yn is minus 1 plus minus 1, then you cover the bigger bracket. You can see that. So when you come here, integral pi to 0 cos x dx will now be equal to, if you say 0.52381 divided by 3, you are going to have 0.1746. 0.1746 in bracket open. Now let us examine this. Of course, you have 1 here plus 4 into, what do we have in the bracket of 4? 0.8660 plus 0 minus that, of course, that will give us 0. Then what do we have in the bracket of 2? 0.5 minus 0.5, it will also give us 0. Then minus times plus will give us minus 1. So you can now say this one is 0, this one is 0, 1 minus 1 is also 0. So this will now give us, or it will take us to having 0.1746 times 0, and that will be equal to 0. Again, using the Simpson's 1 over 3 rule to solve, we have gotten 0. Now our truncation error will now be equal to the true solution minus the numerical solution is 0 minus 0, and our truncation error is 0. That means the Simpson's 1 over 3 rule is error-free for this particular problem. So we have used 4 methods, 4 different numerical integration methods or formulae to solve this problem, integral from pi to 0 cos x dx. You can also integrate sin x dx. You can also integrate any problem on trigonometry. Any trigonometric function, you can carry out integration using any of these numerical formulae. Numerical formulae, you can see that these numerical formulae are highly dependable. They are highly dependable. Now we want to go to the second part of today's teaching, which is the integration or numerical integration of exponential functions. Exponential functions. So this table will not be needed. So we are going to take an exponential function and carry out the numerical integration. We will first of all carry out the integration using the true method of solution, or we call it the exact method of solution. to get our true result. Then we will now take 1 or 2 or 3 numerical methods to carry out the analysis and see how reliable these methods can be in the integration of exponential function. So we shall be using the Boole's rule today. So let us see the Boole's rule first. The Boole's rule. For the Boole's rule, n is equal to 4, and the Boole's rule is given as integral x4 to x0 y dx, that's the Boole's rule we are looking at now, is equal to 2h over 45 bracket open 7 y0 plus 32y1. Remember we used it in our last video, plus 32y1 plus 12y2 plus 32y3 plus 7y4 plus 7y4. So this is the Boole's rule. Now it will interest you to know that for the Boole's rule, here our h is equal to b minus a all over n. Here, of course, our n is 4 for the Boole's rule. Our n is 4 for the Boole's rule. So please, I want to bring up a problem. If I have a problem as this, if I say integrate the upper value to be 1, the lower value to be 0 exponential x dx. If we are told to carry out this integral, it's a definite integral. It's a very simple and innocent looking integral, but carrying it out numerically involves certain techniques. Now, if I want to get the true solution of this, of course, it is easier. The exponential function is the only function when integrated or differentiated, it remains itself. Just like the sine x and the cos x and the tan x, they can be expanded using the Taylor series expansion. When you expand, like we integrated the cos x and we got sine x. When you differentiate the expansion of cos x, and when you integrate the expansion of cos x, you will get sine x. And if we differentiate sine x, we will get cos x. All these are gotten using the Taylor series expansion. Now, let me just prove that to you quickly before we go further. The Taylor series expansion, for exponential x is exponential x is equal to 1 plus x squared over 2 factorial plus x raised to the power 3 over 3 factorial plus x raised to the power 4 over 4 factorial plus, it's an infinite series. Now, if I differentiate this or integrate this function with respect to x, I will have it repeating itself. So it is the only function when you integrate it or differentiate it, it remains itself. So integrating this, I'm going to have exponential x. Then of course I told you that the integration constant for definite integral will definitely cancel out. So there is no need writing it. If it is indefinite, you need to put it. So our upper bound is there 1 and our lower bound is 0. So this will be equal to exponential 1 minus exponential 0. So exponential 1 will be equal to, we are taking up to 5 decimal places, it will be equal to 2.71828. 2.71828 minus exponential 0 raised to the power 0 is 1. So carrying out this subtraction, we are going to have 1.71828. So this is our true solution for this particular problem. Take note of that particular solution. So our true solution is 1.71828. Remember, we have worked or we have solved it up to 5 decimal places. 5 decimal places. That's what we are working with. Now permit me to get the value for, look at it now. The value of h you are using for the y's is different from the value of h you are using. So now let us get h in degrees. H in degrees will now be equal to, of course, pi in degree is 180 degrees. So we are going to have h is equal to the, okay, no, we are not using trigonometric function, so there is no need. We can just go ahead and get the value of x and y. So it is not a trigonometric function, so we are not going to do that. So now let us go ahead and claim the board. Our true solution is 1.71828. Please take that as the true solution. Now we want to use our numerical solution to get this problem solved. Now for this particular one, our h is simple. The problem we are integrating is integral 1 to 0 exponential x dx. So b here is 1, our a is 0 all over 4, our n is 4. So this will be 1 all over 4 is equal to 0.25. So our h for this particular problem is 0.25. It is an exponential function. So here our y will be equal to exponential x. So now permit us to write values for x and y. So x runs from 0 to 1 and is increasing with what? The step length h. So we are starting with 0, increasing it with h is 0.25. The next one will be 0.5. 0 plus 0.25, 0.25, 0.25 plus 0.25, 0.5, 0.5 plus 0.25, 0.75, 0.75 plus 0.25 is 1.0. So we stop. So it's taking value from 0 to 1 and it's from 0 to 1. So we have gotten that. Now we want to get corresponding values for x, for y. When x is 0, note our y is equal to exponential x. So exponential 0 will be 1. So exponential 0.25, we are taking it up to 5 decimal places. It will be 1.28403. 1.28403. Then exponential 0.5 will be 1.64872. 1.64872. Then exponential 0.75 will be 2.1170. 2.1170. Then exponential 1.0 it will be 2.71828. 2.71828. All in 5 decimal places. Permit me to rule it out so that we have this table of values of x and y. We have it like this, and like this. Then we rule the center so that we can locate them easily. So place, here will be your y0 again, here will be your y1, here will be your y2, here will be your y3, and here will be your y4. So for the sake of identification, it is good you do it this way so that it will be very easy for you to identify. So now let us quickly use the Boole's rule to solve this, since we have gotten our table of x and y. So integral 1 to 0 exponential x dx will now be equal to 2h, that is 2 into 0.25, our h is 0.25 all over 45, bracket open, 7 into y naught, y naught is 1, easy to identify, plus 32 into our y1 is 1.28403, then plus 12 into y2, our y2 is 1.64872, then plus 32 into our y3 is 2.1170, then plus 7 into our y4 is 2.71828. Then you cover the bigger bracket. You cover the bigger bracket. It is as simple as that. It is as simple as that. So if you come now and carry out this, you are going to have 0.5 over 45. Do you know why I'm doing it that way? To save me what we call inherent errors. To save me what we call inherent errors. If you carry out all this, you multiply this by 7, multiply this by 32, and you carry out the additions, you are going to get 154 points. You are going to get 154.64556. Then when you carry out that multiplication, you get up to 5 decimal places. You are going to get 1.71828. 1.71828. You can see this is very okay. So our truncation error will be equal to the true solution minus the numerical solution, and is equal to 1.71828 minus 1.71828, and of course that will give us 0. You can see our true solution was 1.71828, and the Boole's rule has given us exactly that particular answer. Now permit me to quickly use the trapezoidal rule to solve the same problem. The trapezoidal rule. The trapezoidal rule. Permit me to use the trapezoidal rule to solve this same problem. It's very important. The table will still be useful to us. Please wait patiently to the end of my class. Subscribe to my YouTube channel, Dr. Chris Esekaibe. Click on the bell button for notification. Like my videos and share my videos on your social media platform. Now let us use the trapezoidal rule. So the trapezoidal rule is very easy to apply. You have it as integral xn to x naught y dx is equal to h over 2 into y naught plus 2 into y1 plus y2 plus y3 plus yn minus 1, then plus yn, then the bigger bracket is closed or covered. So you can see how cheap it is. Now let's quickly go and use it to solve our problem. Our problem again is integral 1 to 0 exponential x dx, and of course our h is 0.25. It will be 0.25 all over 2 into our y naught is 1 plus 2 into 1.28403 plus 1.64872 plus, of course, the third one 2.1170, Then of course you close the bracket, because you can see for the trapezoidal rule, 2 is taking every value of y from y1 to the second to the last y, a value of y. So that's what we have done from y1, y2, y3, then y4 will be reserved, because y0 and yn, our yn here is 4, so it will be reserved. So you now say plus 2.71828, then you cover the bigger bracket. So carrying out all those arithmetic, you are going to have 0.25 over 2, because if you carry out 0.25 over 2, if you carry it out, it's going to give us a long decimal, a long non-terminal decimal. We will be forced to carry out to round off some numbers and cut off some numbers, which is not good for us. So we are going to have, okay, we can also have it as, you now have 1 plus, then when you now have 2 into, you add these 3 values, you are going to have 5.04975, 5.04975, then plus 2.71828. Okay, we carry it, it's going to give us a terminal decimal. So we are going to have integral 1 to 0 exponential x dx, and that, if you say 0.25 divided by 2, you are going to have 0.125. It's not a 0.125, so it's not a non-terminal decimal. It will give us 0.125. Then when you multiply this by 2, add 1 to it and add that value, you are going to have 13.81778. 13.81778. And when you carry out that multiplication, you are going to have 1.72722. Going to be 1.72722. So this is the answer we have gotten using the trapezoidal rule. You can see here that the answer we have gotten is close. So our truncation error will be equal to the answer from the true result is 1.71828 minus 1.72722, and that will give us minus 0.00894. So this will be our truncation error gotten using the trapezoidal rule to solve that same problem. So this is our true solution, and this is our numerical solution. That minus that, so you have that. So you should understand this. I hope the class is becoming interesting by the day. So lastly, let us see how we can use the Simpson's 1/3 rule to also solve this problem. Using the Simpson's 1/3 rule to solve these problems, and at the end of it all, we will do what we call error analysis. We will do what we call error analysis, comparing errors from the 3 methods used. For the trigonometric problem we solved, we found out that the 4 methods had the same level of error. That means they were 0. The errors were 0. That means they were error free. So now the Simpson's 1/3 rule for this exponential function. So we have it as integral xn to x0 y dx is equal to h/3 into y0 plus 4 into y1 plus y3 plus yn minus 1 plus 2 into y2 plus y4 plus yn minus 2, then plus yn, then the bracket is covered. So using it to solve our problem, integral 1 to 0 exponential x dx will now be equal to, note, our h is 0.25 over 3, bracket open. Our y naught is 1 plus 4 into, now what is our y1? Our y1 is 1.28403 plus, what is our y3? Our y3 is 2.117. So we only have y1, y3. It cannot take the last value of y, so we close it there. Then plus 2 into, of course, we only have y2, 1.64872. Then, of course, the last value of y plus, which is the yn, plus 2.71828 plus 2.71828, then you cover the brackets. Okay, let me write it quickly. Okay, permit me to write it under this, plus 2.71828, and you cover the bigger bracket. So coming here, our integral 1 to 0 exponential x dx will be equal to, of course, dividing 0.25 over 3 will give us a very long decimal, so we have to retain it so as to prevent our inherent error. So when you carry out that, you are going to have 1 is here, plus, of course, 4 into this plus this, it will be 4 into 3.40103, 3.4 into 3.4 into 3.401 40103. So when you add this plus this 4 into that, then 2 times that, 2 into that, you are going to have 3.29744 plus 3.29744, then plus the last value there, 2.71828. You cover the bracket. Then of course you are going to have 0.25 over 3 into, when you carry out all those arithmetic, you are going to get 20.61984. 20.61984. Then when you press 0.25 divided by 3 and multiply the answer by that, you are going to have 1.71832. It goes to 1.71832. This is our final answer. Now our truncation error will be equal to, the true solution is 1.71828 minus our numerical solution using the Simpson's 1 over 3 rule is 1.71832, and that will be equal to minus 0.00004. You see that? So that is what you have there. Now we have used that to solve. So lastly, it is good we look at what we call the error analysis for this particular problem. Let us see the error analysis. I hope you have understood this. I hope it is clear enough. You are not a stranger to this method for numerical integration, the Boole's rule, the Weddle's rule, the Simpson's 3 over 8 rule, the Simpson's 1 over 3 rule, and the trapezoidal rule. Now for this particular problem, let us examine error. Now we call it the error analysis. For this particular problem, we have the method and the error gotten. Now, for the first method we used, we use the Boole's rule, and the error gotten was 0.00000. We are dealing with it up to 5 decimal places. That's the error gotten. Then the second method used was the trapezoidal rule, and the error gotten was minus 0.00894, minus 0.00894. And the last one is Simpson's 1/3 rule. The Simpson's 1/3 rule, we got minus 0.00004. Now, beloved, if you look at these errors, you will see that by ranking, the Boole's method is the first position, followed by the Simpson's, and this one is the third position for this particular problem. The problem we solved was integral 1 to 0 exponential x dx, and the true solution is 1.71828. That's what we got as the true solution, 1.71828. So you can see that the one that has the least error is the best for the problem. This one has no error at all, the Boole's rule. Then this one has up to 2 decimal places. You cannot say it is better than this one that has up to 4 decimal places, and we consider error up to 5 decimal places. So the Boole's rule is the best for this particular problem, followed by the Simpson's 1/3 rule, then followed by the trapezoidal rule that has error level of accuracy to 2 decimal places. The Boole's rule has it to 5 decimal places. The Simpson's 1/3 rule has it up to 4 decimal places, while the trapezoidal rule has it up to 2 decimal places. Below, I think we have tried for today. We have done much. We have looked at the solution of trigonometric and exponential function using numerical approaches. We used the Boole's rule, the Weddle's rule, the Simpson's 3/8 rule, the Simpson's 1/3 rule, the trapezoidal rule, and we solved 2 different problems, one from trigonometric function and the other one from the exponential function. A lot has been said, and I believe you have learned a lot. Please subscribe to my YouTube channel, Dr. Chris Esekaibe. Click on the notification button, the bell button, so that anytime I upload a video, you will have a notification or an alert. Share my videos, my YouTube videos, on your social media platforms, your Facebook, your WhatsApp status, and the rest of them. Please be part of those sharing knowledge across the globe. I will be coming again in my next video with the numerical differentiation. Now I want to go back to numerical differentiation of trigonometric and exponential functions. It is good you know how to carry out numerical differentiation also of trigonometric functions and exponential functions. Please wait patiently for that video, and as you do, God will bless you. Enjoy the rest of the day. It's nice having you around. God bless you. Bye.